Here's what we've got. So I've got my light source, okay? Here I have, in this situation, it's stamped on here a 10 centimeter convex lens.
Right.
So the 10 centimeters is giving you the focal length. Okay, that's what that's referring to, is the focal length. So I've got my light source. I've got, in this case, a convex lens, which means how is it shaped? Like that or like that?
The second one.
Convex.
Second one.
Towards the outside, right?
Oh.
Okay. So I'm going to I've got this, my light source, at 10 centimeters. I'm going to put this at 25. So in terms of dimensions, this distance from the source to the lens is going to be, in this situation, my object distance. Okay? Because that's the distance from the source to where the lens is. Okay? Now, I've got another distance from the lens to where I see the image. So this would be my image distance. So this is my object distance. This is my image distance. Now, I can adjust this. So notice as I change that, it goes out of focus, but then eventually it comes into focus. But if I go too far,
Blurry again.
it gets blurry again. So there's one exact spot where that's in focus. But that is not the focal length. The focal length is determined by the structure of the lens. So, like this is at 25, this is at about 55 roughly. So if this is 25, and that's 55, then my image distance would be 30. Okay? So I've got a focal length stamped on here of 10. I've got this distance, which is my image distance. I've got this distance, or this is my object distance. That's my image distance. Now, if I change this, if I bring this closer, okay, I've decreased the object distance. But now I can still make this focus, okay? But now I've kind of got to go way out here to get that into focus. But there's another thing about this. So notice with this one, the 4 here is upright. But this image is inverted. Okay? So that's another thing. So that's why I said sometimes you'll see images that are upright. Sometimes you'll see that they're inverted. This would be an inverted 4. Now, last bit of terminology. What we call a real image versus a virtual image. A real image is something, the short version of this, a real image is something that you can project onto a screen. So I've got, and if you notice the path of this light, this path is going from the 4, it's going through the lens. Now, notice that that 4 is upside down. So when it crosses through that lens, what has to happen, so it's coming in like this, it's going to go through the lens, they cross over each other.
Why do they do that?
That's, we'll get to that. So that's why this is upside down. So how you would describe this is that you would describe this as a real image, because I can project it onto a screen, but it's inverted. So this would be described as an inverted real image. And if I change this, I move this further out, okay?
I think he's going to get to that.
Okay. Now,
Making the 4 really
Yo, why is it tiny?
Wait, can you make it go
You're making it
more
look like
upright?
Riot.
no, can't make it go upright, because it's always going to cross over each other. But now, you'll notice that when this is close, that the 4 is big, okay? But if I increased my object distance, my image becomes smaller. If I go further out, okay, smaller and smaller and smaller. So what you're going to measure in the lab, you're going to physically measure the size of that 4. Now, the other thing that you have to keep track of is the size of the object relative to the size of the image. So the size of the object is a fixed value. Okay, this would be like 2.5 centimeters, whatever that is. So in this case, I've got a big 4, but I'm projecting, and what I'm forming is a small 4. So what would my magnification be? Bigger than 1 or less than 1? Less than 1, because I'm making an image smaller than what I started with.
Right.
Okay? But now, if I move this back, okay, then I can get a 4 that's bigger than what I started with. Then the magnification would be over 1. Okay? Got that one.
Right.
So this is a convex lens that produces an inverted real image. Okay? Got that one.
Oh, I know
All
why.
right.
I know why it does
Okay,
upside down.
so now, let's come over here.
Why? I know why.
Because it's inverted.
I know why. You know why? You know why? It does it because
Oh,
the
you're
light.
optometrists. Yeah.
Oh, I'm so sorry.
The light. And it angles up.
What?
What if you took it like 3 o'clock hours?
There was a point where you just can't bring it into focus.
So you brought
It's
it.
beyond the mathematical limits of what you can do.
Are there multiple points where you can bring it into focus?
Oh, yeah. Oh, yeah. As long as it satisfies that thin lens equation. Okay, so I have a mirror. Okay?
A mirror.
And this could actually like pivot. So here's the easiest way to tell if it's a concave or a convex mirror. If you bring it close and you see yourself like upright, and then you take it further away and then you flip over, the only way that happens is if it is a concave mirror. So that's the easiest way to tell. It's like you have a mirror. Which one is it? I don't know. Hold up close. Okay? If you can see your nose upright, it's a concave mirror. If it's a convex mirror, it will always stay an upright image. Okay?
Right.
But if I can flip it, that means it's concave, which we'll get into the optics on why that works in just a second. So what I have here is my light source. I've got the mirror, and then I'm going to turn that a little bit. Okay?
Whoa.
Oh.
There we go.
Okay. So if you look at the path that this light is taking, it's starting here. Light's going through this opening here. It's hitting the mirror. It's bouncing off of it and forming an image right here. So on this one, the distance from here to here, object distance, image distance.
Whole distance.
Here to here. Object, image.
Object.
Object. Because of the fact that that's how far it's going from here to where the light hits the mirror.
Object distance.
Now, the distance from here to here
Image.
is my image distance. Okay? And again, you would have to be told what the focal length of the mirror is. So, it's coming through, it's hitting. Is this a virtual or real image?
Virtual.
Real.
Real.
Because it's on a thing.
I can project it onto a screen.
Oh, okay.
Okay? I can project it onto a screen. Is the image upright or inverted?
Inverted.
It's inverted. So I've got an inverted image
Just looking at it.
that's upright. Now, what would you guess the magnification
Less than
would
one.
be?
Less than one.
Less than 1. Why?
Because it's a small.
It's small,
Not big.
right? Okay? It's small.
This ain't a competition.
So, now, again, if I change this and move this further out, okay, I can still make it focus, okay? Right? So as I go farther and farther and farther, what's happening to
More like you.
my image distance?
Microscopic.
It's getting smaller, right? So the magnification is becoming smaller and smaller and smaller. Now, if I bring it up close, okay, like that, now the 4 is getting bigger. So I can change this. Now, but no matter what, once that comes into focus, that satisfies the thin lens equation that 1 over psi plus 1 over so equals 1 over f. Okay? Got that one. So, real image inverted. Now, the cool thing about this is if I take this out a little bit, okay, let me get a little bit farther away from here. Get this forward. Is that if you notice, like off to the sides, you can see like the front of the room. Okay?
I can't see it.
Well, you can see it off to the sides, but it's not in focus. So that's kind of like the television. You see like that blue, okay?
Oh.
Right? So this is still taking in light from the entire room, but it's not in focus. Why isn't it in focus? Yeah, it's not satisfying the thin lens equation. Okay? So I can have that, I can kind of see it, but it's not satisfying the thin lens equation because my object distance is
Too far.
Too far
yeah,
away.
really, really big. Okay? It's trying to form an image, but it can't. Okay, now, the next one. Watch out.
So is light a wave or a particle?
All right. Holy one.
Now, this is a concave lens. So this is a hard one to see. So this is a concave lens. So the lens comes in like this. So this is why this is tough to see. Okay? So when that light goes through, it hits this lens. Concave lenses are shaped like this. And I'll show you on the ray diagrams in just a second. So that means that it spreads the light out. Okay, you'll see why that works in just a second. But here's the important part. When it goes through here, this light gets spread out. So if you try and look at it on this side, that light is going like this. Okay? It isn't being brought to a point. It's being spread out. It's tough to see. But what happens, and it's difficult to see, but you can do it. But what happens is that some of that light, even though the light is going in this direction, some of that light gets refracted back into an image that's right here. So if you sit back, and the only way you can see this is if you have to be back on this side. But if you're back here and look over the top of this, what you will see is a floating four, a very, very tiny, and you have to be kind of directly behind it to see it. But what you'll see is a floating four right in front of that. Okay? So what that is, this is a virtual image because I can't project it onto a screen.
I don't see it.
You know that magic set thing where the coin you try to grab it?
That's a virtual image. Okay? So, and you have to get behind this and look over the top. But if you get behind it and look over the top, what you'll see is like a tiny four that's floating in there. So if you do the math of the optics, the light's coming in, some of it's getting reflected back, and it's creating a tiny floating four.
But what's
So you look over the top, and you'll see it like right here.
the little four that's floating? What is it?
It's like
What do you mean?
it's like the little brightest
It's
piece
just
of light
in the
right
air.
there.
Yeah,
What's it being projected on?
it's not.
Air
It's the
part. It's a
intersection
wave.
of the
Nathan, it's a
waves.
wave.
Oh, that's even going to get weirder. We'll get to that
This is
later.
so bad, bro.
Oh, it's going to get
Okay,
worse.
that's hard.
You said this.
Okay, can you see it?
Yes.
Okay.
I'm moving.
So this is an example of a virtual image. So I can't project this onto a screen because if I try to put a piece of paper here, what's going to happen?
It blocks it.
It just blocks it. Okay? So I can clearly see that it's making an image, but I can't project it onto anything. Okay? So this would be a virtual image, and the only way, and certain lenses you can only make like virtual images. This is the classic one. So if you have a concave lens, you can only make virtual images from that. Okay.
So, Burke, how do we see this on a 2D piece of paper?
Oh,
God.
Okay, so watch out. All right. So get where you can see this board. Specifically this board.
Oh, I'm too close.
Okay.
I tried to.
Yo!
So, I've got rays that are being emitted from this, put my hand up there, right? And I can see them because they're bouncing off of my skin. So, you want to do lenses or mirrors first?
Mirror.
Mirrors, okay. So, this is a mirror, okay? And the reflective side is like this. So, is this a concave mirror or a convex mirror?
Concave.
Concave mirror. So I'm going to put this here. And,
Yo! That actually makes sense though.
okay?
It does.
So,
It's like the Death Star, bro.
okay? So notice that what's it doing?
Reflecting.
It's taking that light and what's it doing?
Pushing it together.
Focusing it together. Okay? So as that gets focused, okay, then notice that after it crosses that the lines diverge again. So this is why sometimes you'll get images that are upright, depending upon which side of this that you're on. So a concave mirror can produce an upright image. Gavin? So you can either produce an upright image or you can produce an inverted image, depending upon which side that you're on. That's another reason why you can tell if you have a concave mirror, because it depends on which side of this intersection that you're on.
Whoa, Bert, time out. Why is there light over there?
Huh?
What's that from?
Huh?
Yeah, what is that like?
What's that light from?
That's just some residual that's coming off
That's
that.
the Matrix, bro.
Okay? Right? So I'm just getting part of it.
Oh.
Now, this is,
Convex.
that's a convex mirror.
Yo.
So you've got this surface. So notice with this one, what's the only option that happens?
Spread out.
The light spreads out. Okay? The light spreads out. Notice that these rays never cross each other. But this is where, especially, this will make sense later when we do like the actual ray diagrams. So the reason that with a convex mirror, why you look small is that imagine that your eyeball is out here. Your eyeball is here. So when you see that light coming this way, your eye tries to trace it back to an imaginary origin on the other side. So when you see this, your eye thinks that it's starting on this side. If you see this one, it looks like it's starting on this side. So what your mind tries to do is trace it back to that origin. So this is why when you have a convex mirror, they look small because your eye is trying to trace it back to a point. Okay. Lens, concave, convex.
Concave.
Concave, why?
It's inside.
Look at the sides. They're both coming in like this. So, with this one, what's it doing? Lines are coming in and then they get
Spread out.
spread out.
What's the difference between this one and the last concave?
Huh?
Mirror.
So, that was
Oh, we're learning.
a concave mirror. This is a concave.
Clear mirror. Wait, clear.
No, this is a lens. That's a mirror.
Concave
That's a
lens.
convex
Okay. So, this is a concave
Lens.
lens.
Mirror.
That is a concave
No, that's
excuse me,
convex.
convex. So this is a convex mirror. This is a concave lens. Okay? So notice when this light comes in, what does it do?
Spread out.
Disperse.
Spreads it out. Okay? So what's going to happen, if I move this a little bit further away, so if I move this a little bit further away, this is that, what I just showed you where you had that virtual floating four. So what's happening is that part of this light, and I can't do it on this because I'm limited because I have to be in the plane of the board. But what happens is that some of that light goes through, but some of it gets refracted and reflected back along this line. And that's why you saw that floating 4. Because most of the light goes out, but some of it comes back. Okay, and that's why you'd see that. Now, this is the classic one. So this is a concave or convex.
Convex.
Convex,
lens.
and that is a
The Death Star.
That's pretty.
that's a Death Star. Okay.
Yo, that's real cool.
Now, so what do these rays do?
Converge.
Do they converge or diverge?
Conversion.
Converge. Then
Okay.
go back out.
So they bring them together. Now, listen to me very carefully. The biggest thing that you have to decide is the focal length. Sometimes focal lengths are positive, sometimes focal lengths are negative. The basiest way to remember this is in terms of like human interactions. Okay? If someone has a positive personality, they tend to bring people together. Okay? So a convex lens has a positive focal length because it brings the light together.
Okay.
Okay? Now, a concave lens,
They're negative. They want to shoot people out.
yes,
They suck.
so they're negative, and it pushes people away. Okay? So, if that light is getting spread out, that's negative. Like, hey, it's negative personality. You don't want to be around them. You divide people. This one brings them together. That would be a positive focal length. That one drives them away. Negative. Now, you have a concave
Mirror.
mirror. What's it doing with the light?
Converging them.
Bringing it together.
Positive.
So that would have a positive focal length
Oh.
because it brings it together.
Oh, yeah.
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 But if you have,
Yeah, that's a negative.
that would be a negative. Why?
Is this shooting you guys out?
Light's being spread apart. Okay.
Fucking zombies out.
So here's what I want you to see. So this is a convex mirror, and it spreads the light apart. So this would have a negative focal length. Okay? So this is why I said there's a whole bunch of stuff you need to keep track of. So a convex mirror spreads light apart. But so does a concave lens. So this is why you can't say, oh, anything that's convex is positive, anything that's concave is negative. Okay? It's not true. What is true is that if the light gets spread apart,
Negative foci.
Are you looking at me?
yes.
Let's go, Nathan.
Is there a bad guy?
So a convex mirror or a concave lens has a negative focal length. But if you have a convex lens or a concave mirror, those have positive focal lengths. So that's why I said you cannot say, oh, everything that's convex is positive, everything that's concave is negative. It depends upon what it does with the light. Got it? Good? Brand?
Got it.
Back we go.
Good.